Welcome to our presentation for infrastructure for photorealistic imaging environmental synthesis. My name is Tansera Martinez, and I shall be also presenting the work that I have been doing alongside my professor, Ryan McMahon. In recent years, we have been noticing that there have been many data sets containing images, videos, and environments. They're the ones that we have found that to be photorealistic and captured by real-world cameras have been small, while synthetic sets that have been rendered from virtual environments are large. Therefore, we identify that there's a need for large photorealistic datasets that can advance and enable research on 360 videos and quality experience, computer vision, machine learning, multimedia systems and networking, for robotic in simultaneous localization and mapping testing, and virtual reality and mixed reality. Our contributions from the I-SPIES project are as follows. We present a pipeline for synthesizing an unbounded number of photorealistic images and metadata images, e.g. such as thematic labels, from terrestrial laser scans of a real-world environment. We developed Recorder Cloud as an application for improving the photorealism of a captured point cloud or semantically coordinate. We also utilize tools that are either open source or free to the educational community in order to make our impact as broad as possible. Our pipeline is detailed as follows. The first step is to obtain a real-world location as a laser scan. Following that is to clean up the captured point cloud utilizing tools such as Autodesk Recap. Following that, we segment the point cloud utilizing Label Cloud. We then polish the point cloud utilizing our new application, Recorder Cloud. And finally, we render our photorealistic images utilizing Autodesk 3ds Max, utilizing the Arnold ray tracing renderer. As the first step on our pipeline, we went to a real-world location called Grid Row and laser scanned it using a laser scanner. After we collected the data points, we stored them in a file format known as .pets and edited it using Autodesk Recap in order to remove any straggling points and any points that were too far from the laser scanner when we ran it. This was in order to avoid any artifacts or distracting elements from appearing in the final images. After cleaning up the point cloud, we then segmented utilizing Label Cloud. This process was done by hand utilizing the tool Label Cloud, and since our dataset was outdoors, we utilized the Kitty labeling system in order to provide more universal transitions for the segmentation. During this, we created bounding boxes that encompass the elements in the environment and then could be utilized in other applications such as Recorder Cloud. After segmenting the point cloud, we then polished the point clouds utilizing our own application, Recorder Cloud. Recorder Cloud allows users to record or delete poorly captured points using algorithms in order to improve the photorealism of the cloud. Recorder Cloud can also record points according to their semantic labels, e.g. such as kitty. And finally, our tool can also segment a point cloud down to its individual labels. In this screenshot, you can see the original dataset from the laser scanner without any modifications. After which, this is the polished photorealistic point cloud, after which we utilize Recorder Cloud to modify the point cloud in order to remove any distracting artifacts from the trees. A recording technique that we have currently implemented is known as median sphere. This is a recordation technique in which a sphere is placed in the RGB space centered around the median of all the RGB colors from inside the label bounding box. Colors that are kept inside a specified radius are maintained, while points that are outside the sphere are recolored with colors that are inside the sphere. In this example, on the tree, You can see that there are certain particulates that are blue, which are different from the rest of the tree, and we just utilize the median sphere in order to record those points to be green just as the rest of the tree. This was also applied to the rest of the trees that are inside of this specified world, similar to the previous images. One current technique that we also have implemented is also recurring and deleting points utilizing bounding boxes. And one such case, for example, where can also recolor the trees as previously shown utilizing bounding boxes. This rescales a bounding box from the extremes, for example, the lowest colored point from our trees, which would be a dark green, to the highest point, which might be white or light green. In such cases, we then rescale that bounding box down to a bounding box that is specified by the user. In this case, a user specified to recolor the trees into the RGB space of red. And as such, what happens is that the colors are then recolored down to be of a reddish tone and hue, and as shown here, the trees can appear to be in autumn or a similar theme. On this slide, we can show how recoloring cloud can recolor a point cloud utilizing the semantic labels. For example, in this case, we can show the application in action. The first action that a user will take will be to load the point cloud. This is simply done by a file system manager and then waiting a little bit for the file to load in. After the file loads in, the user then gets the bounded boxes from label cloud and then puts it into the system. After which, then they will utilize a tool, text file that has the semantic labels already written out. These labels will be the ones that are matching from the bounded boxes. So, for example, if a building was to be yellow, the file will have the RGB values for yellow inside of that text file. Then user then goes and selects to create a semantic version of the point cloud, and then they will wait a little while, after which they can then produce the semantically segmented point cloud from the original data set, and after which they can then export the point cloud. Another example that we have implemented is segmentation utilizing semantic labels. In one case, for example, since we're already utilizing the kitty labels, we decided to remove the vegetation and the tree trunks from the trees. Users may be disliking all of one case. For example, they need to quickly produce a map that just has buildings and light posts and any other general item and no trees. They can simply specify to remove all of the vegetation or all the trees and quickly produce a new point cloud with all of those items removed. This is in contrast of going inside of a tool such as the Autodesk Recap tool, which may not be as efficient to remove all the items at once. The final step in this pipeline is the 3ds Max rendering. This is done utilizing Autodesk Arnold, and in such case we are giving the users a camera rig for producing renders, in which case they have the option of 360 rendering, monocular rendering, which one camera is involved, and stereo camera, in which two cameras are involved in the rendering process. Additionally, they can render the semantic point cloud, in which they have previously already produced labels and recolored it, or they can bring in their own point clouds, in which case this is called the realistic point cloud. On this slide, we can see a couple of renders. So starting from the top left, we can see the semantically labeled point cloud being rendered. Next to it is the depth from the camera to the world. To the bottom, you can see the realistically rendered or photorealistic renders. In this video, we will see the photorealistic render as it appears from Arnold's 360 view. So as we can see here, the trees and the buildings appear to be photorealistically scaled, and the floor also appears to be scaled correctly. And if we were to try to pass this through a computer vision algorithm, it will be more likely than not that this will appear correct to it. In this video, we will see the semantically colored point cloud. As we can see here, we can see the tour of the same location, the same motion, and we can see that the colors from the trees and from the floor, everything appears to be colored as expected using the Kitty labeling system. Finally, on this video, we can see the depth rendering as seen from the camera motion. As we can see here, we can see the depth and the distances from each of the buildings and also from the trees, and it appears closer or farther away from the camera. So some of potential applications of our pipeline are as follows. Essentially, we have created the ability of synthesizing controlled photorealistic 360 videos for research. In such cases, our videos produce zero jitter or can be controlled in such a way to avoid sickness, which are kind of, for example, present in certain drone videos in which the camera is shaking or vibrating in such a way that they produce cyber sickness. And we can also produce scenes with explicitly controlled objects. For example, if we want to have one item being a target or moving object, we can specify that that object exists, as well as any specified object such as a car, person, etc. Finally, we can also produce photorealistic 360 videos with semantic counterparts and depth counterparts in order for view predictions and any other application. The synthesis of this can also extend to other types of photorealistic images and videos, such as monocular images, stereoscopic images, depth images, and other types of cameras that we may not have applied yet. So finally, that concludes our presentation. The following is my contact information as well as from my professor. The following material is supported by the NSF using the following grant number. And thank you for watching.